prime goal is to make sure you do chemistry which is useful, okay? And I think I must thankful to Wilfried also, like his organization is now using our chemistry, okay, on a wide variety of reactions. Okay, this is one of the industry. Hopefully, he will show you more data and then tell about other industries how they are now interested to do chemistry in water and why they are interested also. So back to the introduction. Dr. Wilfried, he did his master's with Barry Trost at Stanford University, and then he moved back to the Germany to University of Hannover, and where he received PhD in 1999, and immediately I think he got job in BASF, and it's one of the big, I think, chemical company in the world.
Yeah, it's the largest.
Largest company in the world, and then he got better opportunity, I think, and then they merged their section to Abbott Pharmaceuticals, now it's known as AbbVie, and he has over about 20 years of experience to work in pharmaceutical industry. He's dealing with a team of postdocs, okay, and then senior scientists, and not only the synthetic chemistry team, also neuroscience and some mass spectrometry and NMR team. He will basically, you know, when you do any kind of organic transformation, typically your reaction time is anywhere from few hours to several days. And yet, I think his chemistry is not published, but he is the person who brought reaction time to few seconds. As soon as you mix components, reaction is done, and it is in water, okay, and super clean reaction, okay. And we recently established collaboration with him, and we will find out using his material why reaction is so fast, okay, and how we can even improve it, okay. So, well, I will not spend more time, and he should start his talk. And as I said, like the title is Organic Chemistry in Water Applications in the Pharmaceutical Industry. Okay.
Thank you very much. Thank you very much, Sachin, and thank you very much for showing up. I think we really have some compelling data which we believe are transformational for the industry. So I will be able not to share, of course, everything, unfortunately. So we haven't published this yet. We have a patent application also on this process. But I can also share the pain that Sachin just laid out, that when I started with my first postdoc 5 years ago, doing organic chemistry in water, the skepticism in the organization. But still, this is actually part of what we should be doing as an industry. I think we have realized that how we do chemistry is maybe not sustainable. I will show you some data, how much waste is generated for the little product we get out in the end. So across the industry, there is actually, now the recognition that doing green chemistry is something the whole industry should be involved with, because it's we have to be more sustainable and we have to be in sync in nature. The processes need to be safer, more efficient, and by that actually, and that's the incentive for our management, is we can save money actually if we apply green chemistry principles. And that's recognized actually by the ACS Green Chemistry Pharma Roundtable. So that means now this is from 17, now actually the top 15 pharma companies are all in this Pharma Roundtable. We meet twice a year. Last week was a meeting at Pfizer at the headquarters, where we actually share pre-competitively new technologies. And the goal is to also reduce the risk to humans and also minimize the environmental impact of what we are doing. So this is just one aspect of green chemistry. So in the pharmaceutical and generic industry, we produce about or greater than 100 million kilograms of active pharmaceutical ingredients per year. And about 150 kilograms of waste is produced per 1 kilogram of API. So if you do the math, that brings you to 15 billion kilograms of co-produced waste, and that's only waste. It's not considering that you have to buy the material also that you use in excess. So only the disposal costs are $30 billion US. And of course, there's lots of potential how we can save these $30 billion. Also, the beauty is actually, and I will show you some data later actually, that you can apply these green chemistry principles across the value chain from early drug discovery to manufacturing actually. So basically, and that's important for my management. It's about efficiency and saving money in the end. And actually, this is a fun slide that I just actually for this presentation is new in my slide deck. So this is palytoxin actually, and this is a drug that was actually discovered by Richard Moore. I did my undergrad at the University of Hawaii working with Richard Moore. It's a highly complex natural product. And if you look at the synthesis, which was a major achievement and milestone by Professor Kishi from Harvard University, it takes about 129 steps. And it's a pain. I guess many graduate students had a very miserable life for quite some time, actually. So that was done in the lab. If you look to nature, actually, it's done in many microorganisms, actually. Palytoxin is being produced. And actually, the native Hawaiians use palytoxin for spearfishing as a poison. So if you look at the efficiency and how nature is doing chemistry and how we do chemistry in the lab. So I just have a few aspects here. So if you look at the solvent for this synthesis, or what we do generally as organic chemists is we have many different organic solvents. These are our working horses. In nature you have only one solvent. It's very simple. It's water. That's all. Also in our bodies actually. It's a very simple system. The temperature range usually in the lab is from minus 78 to 130. In nature, it's always the same temperature. It's ambient. If you look at the complexity, it's very high because you also have, you set up the reaction, you process the reaction, you have to work it up, you have to purify it, and then you do the next step. In nature, this is done in one pot. Reaction times. It's usually hours, so it's pretty slow. If you look at reaction times in nature, when I speak now, my neurons are firing. Within split seconds, millions of chemical reactions are happening. If you look at the catalyst, actually, in nature, you need trace amounts, and Sachin has done an excellent job of showcasing how to do this for palladium-coupled reactions. In the industry, we still use percentages, and if you think about at what time we will be exhausted the palladium, it's not too far in the future that we may not do palladium couplings because there will be no palladium left. Also, when we look at the waste, actually, it's almost zero because nature cannot afford to produce all the waste because otherwise we would be dead within a few minutes, actually. And if you look at the methodology per se, in nature, the methodology has been optimized since billions of years, so it's highly optimized, whereas in the pharmaceutical or chemical industry, since the past 150 years probably is how this was optimized. So when it comes to chemical synthesis, the efficiency of nature is really unparalleled. And actually, that's the topic of the talk is, we want to talk about the chemistry in water. So since organic solvents account for 50 to 80% of the mass that's being utilized in a chemical reaction, there are, of course, ups and downs. Why do we use actually organic solvents? Because we need to solubilize our starting materials, and that's actually the key point. But this comes actually at a price, because most organic solvents are harmful and toxic. They pose not only a significant risk to the environment, but also actually to you guys and to me actually, because we have to work with these solvents. They are hazardous, so they have a lot of unfavorable properties. In addition, also, you have to buy them. They're quite expensive, and then at the end of the reaction, you have to dispose them. So you have double costs, actually. And they're also the reason for the high waste generation. But why do we use organic solvents? Because they solubilize our starting materials. Otherwise, we believe that we cannot get chemical reactions to work. On the other hand, water is non-toxic, non-flammable, or explosive. It's cheap, readily available, but it has poor solubility properties of organic compounds. But in principle, water would be the ideal solvent. So the question is, how can we combine these two worlds? And this is also a new slide, actually, that I just put in. It's actually, nature teaches us already how we can do this. This is a lemon, actually. And limonene is a terpene with a really high C-log-P, so it's like a hydrocarbon. So it's highly insoluble in principle in water, but still nature is able to solubilize limonene. So there's a lesson we can learn from nature. And there are also many other strategies that nature is using actually in our bodies. So bile acids actually is the mechanism how we can process fats in our bodies. So that's another layer of what we can learn from nature. And then, of course, the story continues when I actually saw this review article from Bruce Lipschutz, actually, in 2012, that you can actually do a lot of these couplings in these vitamin E-derived surfactants, which form micelles in water, actually. And the beauty is you can do this at ambient temperature, which is nice because usually if the reaction temperature is low, the reaction is much cleaner. That saves you a lot of time in the end. What really caught my eye then is actually that you can do Negishi couplings in water. Because that's so, to me, it's so counterintuitive because I learned you always have to keep away the water because it kills your Negishi reaction. So I was really intrigued actually, and that's how we got started actually in this field. Before I go into the more details, actually, I just want to outline a little bit of the scopes and limitations when you work in industry. So personally, I work in medicinal chemistry, but if you move from the milligrams to the kilograms, that's in process chemistry. And I just want to outline a little bit of what the differences are, and that it would be great if we have a methodology that actually captures both sides, the medicinal chemistry part, but also which is amenable for process chemistry. So the mission for medicinal chemistry is fast access to multiple compounds, and process chemistry, efficient synthesis of one single compound. So the goal for me right now is to prepare less than 5 milligrams, usually 5 milligrams with a high purity, or with a reasonably high purity, let's put it that way. 95% is perfect. In process chemistry, it's more than 100 grams, usually it's in the kilogram range, and with high purity. The objective is, in medicinal chemistry, fast and flexible access, high success rate of reactions, fast setup, workup, easy product isolation. Would be great if you can simplify the operational aspect by no need for an atmosphere, and that is amenable for high throughput chemistry. Whereas for process chemistry, it's reliable and cost-effective methods. Again, also like here, high success rate, clean reactions, high yields, no chromatography would be great. Trace metals would be acceptable, but also here, no metal traces in the API. And of course, minimizing the waste. So ideally, we would like to have a technology or a methodology that covers these aspects from milligrams to kilograms. And we believe actually, well, that's initially when I saw the papers from Bruce Lipschutz, actually, I was intrigued if this chemistry in water actually can achieve this. This is also something that actually caught my eye again, is that you can actually do a one-step, a one-pot reaction sequence actually, very efficiently. So it's 5 steps, 1 pot. And don't want to go into much details, but again, work from Sachin on the nanoparticles, really great stuff, because in the end, you don't want a lot of palladium in your final product. And this was 5 steps, 65%. Also, I like this one actually. First, that this one got published actually, because if you see, I mean, there are stars and circles and bananas actually, so don't actually really, they didn't disclose any of what was going on, but still was published actually. But to me it's a major achievement because it's the proof of concept that the chemistry in water can be taken from milligrams to process chemistry actually. And also you can see already that you don't need excess of starting materials, which is really important. It cleans up the reaction. It's, I mean, from the economics, it's much, much better. And that's also why this is a landmark paper to me. So proof of concept that you can actually do this chemistry in water on kilogram scale, which was a big skepticism in my organization actually. So that was achieved. Also looking then at the advantages actually. The yield actually was improved from 42 to 48. It doesn't sound like a lot, but if you do this on a 100 kilogram scale, this actually adds up. And then what's really nice is the shorter total reaction time, because it's almost in half. So that means you can use that reactor for something different. So that saves a lot of money. Which is also really interesting is actually that you get higher quality of API. That's really important for us because we need highly pure material in the end. And also the uniformity of the product is improved. The waste was 50% less, and that of course leads to much lower cost. What is great about this technology in general is actually that you don't need to change anything. It's just an alternative solvent, so it shouldn't hold you back actually from trying this out. And what I thought is interesting actually, this quote from Novartis actually, that it triggered a shift in the paradigm actually to look much deeper into this technology. But this was the first time that this was done on large scale in the industry. So that's how we got started with my postdoc. Actually, we wanted to assess the reproducibility, because I've seen many technologies in my past 20 years where there are great publications, once you try it out yourself, that you run into severe problems. So that's why we had actually, my first postdoc, we used some of the most common reactions, Suzuki, Hartwig, Sonegashira, the Gishi-like couplings. And what was interesting, actually, I had actually apprentices, interns, trying out different reactions. And every time, actually, what I had never seen before, it all worked in our hands, actually, which I thought was really cool. Because everything that makes your life easier and more simple is great. So after we achieved this first assessment of literature that we can reproduce, of course we want to extend this to our in-house problems, and also to reaction types that at that point were not published.
So all these conditions were we published?
Exactly, that's everything that you and Bruce Lipschitz actually published. And this is actually something, we want to do the same exercise with this consortia where all the pharma companies actually will do the same exercise, just to show, because that would be for the first time where 15 of the biggest pharma companies do the same reaction, and then we compare what the outcome is actually. This would be really interesting to see how reproducible actually literature is, especially for this methodology. So this is just one example actually from the early days. So we did this Suzuki coupling. This was the original, it was also PTS, so it's really old school, so from 2008. And then my associate did this on 5 milligram scale. And actually I thought this is also nice that actually you can do this on a small scale, because oftentimes we don't want to waste a lot of our starting material, it's quite precious, if this works on small scale. And this is just the crude mixture, reaction mixture, no workup, but it shows you that there is a clean peak here. So it was nicely reproducible. So we didn't even bother to isolate it. So I would think that this is highly reproducible to me. And here I want to point out, because it's part of the story why I'm here actually, and want to collaborate with Sachin later in the talk, is the Backwell-Hartwig reaction actually. Here, the only side product, the major side product, was actually the ligand after the extraction. So that's one thing, as you will learn later, is actually we want to, usually now, our reactions are so clean that we don't need chromatography. For the Backwell-Hartwig, the only contamination after workup is the ligand. So actually Sachin will use our surfactant and immobilize the ligand on HPMC, which is our surfactant. And then actually we will get very clean conversions. So that's part of the reason why I'm here. So the lessons learned actually which was great, because experimental setup and execution is very easy. Also, I will show later in the Gishi type coupling, which is great because you just dump all your starting materials in the vial and then just add the water to TGS, let it stir, and you get your product. I mean, it's operationally very simple to preparing the zinc organelle in a separate flask, having it funneled over. Also, the workup was easy, that it can be, it's amenable in principle for high throughput experimentation and high reproducibility, at least in our hands. What is one of the key lessons is that the ligands used in micellar catalysis are very different from those used in conventional chemistry. I had actually a lot of discussions with my colleagues when they tried something. They always use what they use in organic solvents, and then you're up for failure because the rules are different. So that's another thing why I think that's why I like to talk about this, because we need more people actually working in this field so that we can derive the rules and be more rational when we pick ligands or conditions. But the initial results are really very promising, and that's why we further investigated. And this is now real-world examples. So this was one of the Negishi couplings that we did. First, of course, we had to prepare the zinc organelle in a separate flask, and then with regular reaction conditions, 13 hours, 80 degrees, 53%. I mean, in a medicinal chemistry environment, this is good enough to carry on, but if you have something that's better, the better it is, and especially operationally. So this was one of the first examples in my postdoc, where you can start with just the alkyl iodide actually. So you don't have to preform the zinc organelle, you dump everything in the vial, and we got even better yield. So that's great, of course. So the advantages here was higher isolated yield, easier to handle. Also, no inert atmosphere was needed, actually, and no pre-formation of the organic zinc reagent. So this is great actually for students or interns. I always like to have them reproduce this because it's it's so counterintuitive for what you learn in university that the Negishi reaction has to be really taken care of and it has to be really dry. This is just a Suzuki reaction that we did for a project that was going on for some time. In the old days then, actually, you always had to use an excess of the boronic acid. And of course, once you isolate the product, there will always be 0.2% of your boronic acid in your crude product, and which leads then to maybe purification problems. The yield also here, when we moved from the conventional conditions to the Micelles, actually was improved from 83 to 93. So here, superior yields to the couplings in organic solvents. And also what is published from Bruce and Sachin is the product isolation is actually super easy. You just add water, and because this is so lipophilic, this crashes out. So it can't get any easier than that, actually. And so it saves you a lot of time also operationally, because where I work, the most important costs, or the highest costs are actually the people that are doing the work. And if you can simplify these processes, if they don't have to clean up something, that improves, they can do something else and be more efficient and faster. But also the mild reaction conditions is always something that I find really striking, and of course is always helping. This is just an old school example actually, and we have now many more examples which I find really intriguing is that we can get chemical reactions to work that in organic solvents fail, but they work either in the Micelle, with the TPGS approach, or with our approach, which I think is adding a lot of value, because if I can get a reaction to work that I couldn't get to work before, that saves a lot of time, because then I don't have to go through another route actually to isolate the product. I mean, here the yield was not great. It also took 3 days, but in a medchem environment, just to get 2 milligrams at the end of the day, that's good enough. So here the problem was actually that we get either, these are not the most stable guys in the alkyl environment, either decomposition here or debromination. So that was the problem here. This was another example of a Sonogashira reaction that we just couldn't get to work. This is just one example of what we tried actually. We just couldn't get this Sonogashira to work, and then actually we just gave it into the Micelle approach. Also here what was nice is, again, that you use a 1-to-1 starting material ratio, no excess, 48%, really good enough. This was something where the stability is an issue, because if you heat this reaction up here, so this is a Hayashi type 1,4 addition, so basically this bond is being formed first and then it's being cyclized. But if you try this in organic solvents, due to the high temperatures actually, and this was actually published by Steve Marston in collaboration with Glaxo, because this is desirable for building block for medchem applications. So you see that the methyl worked reasonably well, but if you move to the phenyl here, you get no product because this is being dephorylated. So this was actually our first entry point where we published something, and you can see that with the methyl we get 95% and with the phenyl 78%. So that was the start. Actually, this is a compound, usually in pharma you add fluorines, that always helps the properties to get drugs more stable. So we actually had this compound outsourced to 2 different organizations that were supposed to deliver this compound, but they just couldn't get the synthesis to work actually. There was only one literature reference where this compound at that point was published as a side product with a yield less than 10%. So that's why we thought, okay, this is a really nice example where the micellar chemistry could hopefully help us. So this is just a summary, and this is pretty much what everybody has seen in the field, that if you use no surfactant, you get some conversion, 50% to the product. Then we tried different surfactants with some success, but the best at that point was really TPGS. And I'm sure that now if we use FI 750M or something, that you come up, I'm sure this can be further improved. So the surfactant TPGS really gave the best results. So we were able actually to use this methodology to come up with some analogs, actually also sometimes really nice, these oxetanes, they're not that stable, especially under acidic conditions. Also you can actually form quaternary centers actually. And again, the ring closure you can speed up. You can speed up if you increase the temperature here, then this can be done faster. So overall, we had access now, and easy access actually, to products where two clinical research organizations actually failed to prepare these compounds. And yeah, it also gives you access because due to the mild reaction temperatures that are otherwise prone to decomposition. This is just, again, showing, but I guess I'm teaching to the choir here, how easy this is, because the setup is really that you dump everything, all your starting materials in the vial, you add the TPGS water, and then you have pizza, and then you come back, and then the reaction is done, actually. And there's also, you can see, actually, the workup here is really easy. Just a little bit of ethyl acetate, and this is where your product is. And it's a really clean reaction. So that's why I love, also this is very, very good for interns. Actually, you don't have a lot of experience in the chemistry labs. This is another example where we have now more, unfortunately I can't talk about this, but this is a typical reaction of sulfonylation actually, and usually the solvent is dichloromethane, which is one of the words when you think about the environmental impact actually. 12 hours, the yield is great, but also you need like DMAP as a catalyst. This was just our first start actually, and we got 99%, and we actually didn't need chromatography. And also, at this point, was only 3 minutes. We have, with our process, optimized these sulfonylations. We're down to seconds now. So it's very, very efficient. So, concluding for this chemistry in water with using Micelles before I turn to our own methodology. So, what is great is simplified and fast reaction setup, execution workup. No need for sequential addition of reagents because you can just dump everything at the same time and then leave for lunch and then come back and do the workup. And also what's nice actually, you need lower amounts of catalysts, which is important for process chemistry. Yeah, the reactions can be run at ambient temperature. Sometimes we move to 40 or 50 degrees, but that's still better than anything what you do in organic solvents. Because that leads to cleaner reactions and then leading to higher yields and easier purification. What's also important is actually that the reactions are scalable, so it doesn't really matter if you do it on milligrams, because you work in the nano world, you can do it on grams or even larger scale. There are not these scaling factors that you usually encounter when you move to larger scale. And again, the methodology can be implemented in any lab or plant, so I think that's great. And of course, not all reactions in water work with Micelles, but it's worth a try, and especially those when you fail actually are not my favorites actually, because now that's where we can learn how to improve this methodology. So that's why the conclusion here is that chemistry in Micelles is well suited for the application in the pharmaceutical industry, because it addresses the key needs in medchem in the milligram, but also in process chemistry where you would think about the kilogram scale. So now I want to move to our own methodology. So addressing the key problem is the poor water solubility of substrates. And one of the solutions, as we have seen, is a Micelle technology from Professor Lipschitz and now also from Sachin, where you use these designer surfactants, TPGS, NOC, and I should add probably FI7050M here. So there's a lot of literature now out there, and Novartis has adapted this technology, so there's a lot where we can leverage on. So actually, we thought that in the pharmaceutical industry, we have the challenge that oftentimes we have drugs that are very insoluble in water. And if you take a tablet like a brickstone, it will just go through your system and no drug will be absorbed. So we have to find strategies how to make insoluble drugs soluble so that your body can actually take these drugs up. So that's why I turned to my colleagues in formulation sciences and asked them for their feedback actually. And by doing that, actually we had some serendipity, I would say, and we actually identified this polymer. So that's also conceptually very different. In Micelles, you have single components, single molecules that form a micelle. Whereas we use a polymer, and that's actually from cellulose derived. And it's one of the working horses. It's HPMC. It's one of them. You almost find it in many of the formulations for drugs, actually. And of course, the idea was actually to benchmark